All right, let's talk about the computer. You've got one on your desk, maybe one in your pocket. Today, we're going to crack that familiar box open and really understand the magic that's happening inside. We're going to demystify the whole thing, from the big ideas down to the tiny parts that make it all tick.
I mean, think about it. We use these things for absolutely everything. Work, talking to friends, watching movies. They're everywhere. But when you click that mouse or type out a sentence, have you ever stopped to wonder what is actually going on under the hood?
That's the big question we're going to tackle. We're going to peel back all the layers and look at the basic principles, the most important components, and the incredible story of how we ended up with the device you're using right this second.
Okay, so to even start, we have to get one crucial distinction straight. When we talk about a computer, are we talking about the idea of it, the design, or are we talking about the physical nuts and bolts? Well, it turns out there's a name for both.
Think of it like this. Computer architecture is the architect's blueprint. It defines what the computer does, the rules and instructions a programmer gets to use. But computer organization, that's the contractor's plan. It's how all those rules are physically built with actual hardware. So you've got the what versus the how. So, with that blueprint in mind, what are the absolute fundamental jobs that every single computer is designed to do? I mean, from a giant data server down to your little smartwatch. It really just boils down to 4 core functions. Yep, just 4. First, you've got data processing. That's the raw number crunching. Second, data storage, which is just holding on to information, whether it's for a second or for years. Third, there's data movement, which is all about getting information in from the outside world and sending it back out. And finally, you have control. That's the conductor of the orchestra, managing all the other functions. Seriously, that's it. Every single thing your computer does is just some combination of these 4 jobs. So to pull off those 4 big jobs, a computer needs a team of physical parts all working together. So let's pop open the case and meet the crew. And hey, just like there are 4 main jobs, it turns out there are 4 main structural parts that do all the heavy lifting. Let's take a look at how they all work together. First up, the star of the show, the CPU, or Central Processing Unit. This is the brain of the whole operation. It's in charge of everything, reading instructions and doing all the math. This is the component that handles those control and data processing jobs we just talked about. Next, we've got main memory. You probably know it as RAM. Think of this as the computer's temporary workspace, its short-term memory. It handles the data storage job by holding on to whatever data and programs the CPU needs to get to, like right now. But the key word here is temporary. Turn the power off and poof, it's all gone. Then there's I/O, which just stands for input-output. This covers all the data movement. It's how the computer talks to the outside world, taking commands from your keyboard, sending pictures to your monitor. You get the idea. And finally, the crucial piece that holds it all together, the system interconnection. This is basically the communication network. You'll often hear it called a bus, that lets the CPU, the memory, and all the I/O stuff actually talk to each other. Without it, you just have a bunch of really powerful parts sitting in a box, totally unable to cooperate. So, that's the modern computer in a nutshell. But how on earth did we get from machines that filled an entire room to these sleek little things we carry in our pockets? For that, we've got to take a quick trip back in time. See, the history of computers isn't some slow, gradual crawl. It's a story of huge, revolutionary leaps. We call them generations. Each one was defined by its core technology, and each one brought insane changes in size, speed, and cost. The first generation, back in the mid-40s to the late 50s, was built with vacuum tubes. Just picture thousands of little glass light bulbs that could act as switches. They worked, sure, but they were massive. They generated a ridiculous amount of heat, and they were famous for breaking down all the time. But then came the transistor. This was a total game changer. Invented at Bell Labs in 1947, this tiny little solid-state device did everything a big, hot vacuum tube could do, but it was smaller, way cheaper, used way less power, and was so much more reliable. This kicked off the second generation and pretty much changed everything. The next giant leap forward was the integrated circuit. Instead of having to wire individual transistors together, engineers figured out how to manufacture them and all their connections all at once, on a single tiny piece of silicon. This is where the true shrinking of electronics really began. Now, this explosion in power and this incredible shrinking act didn't happen by accident.
It was actually driven by a surprisingly powerful observation that has basically been the guiding principle of the tech industry for over 50 years. It's called Moore's Law. Back in 1965, Intel co-founder Gordon Moore noticed that the number of transistors they could cram onto a single chip was doubling roughly every 2 years. And the incredible thing is, that trend held up for decades. It became a self-fulfilling prophecy, a target for the entire industry to hit.
And the consequences of this exponential growth were just profound. As you pack more transistors into the same space, computers get dramatically cheaper. The electrical paths get shorter, which means they get faster. And of course, everything gets smaller, more power efficient, and a whole lot more reliable. This is exactly why the phone in your pocket is more powerful than a supercomputer from a few decades ago. It's also why that top-of-the-line laptop you bought 5 years ago already feels kind of sluggish, right?
And this right here shows you the result. On the left, you're looking at a computer motherboard from around the year 2000 with all its distinct, separate components. On the right, that's a modern processor. Billions, with a B, of those same types of components are now all squeezed onto a piece of silicon smaller than your thumbnail. That is Moore's Law in action.
So this leaves us with one last kind of mind-bending thought. We have gone from room-sized machines to pocket-sized supercomputers in a single lifetime. If this incredible pace continues, what becomes possible next? What problems will we solve? And what will our world even look like when today's devices seem as ancient as a vacuum tube?